Okay, so that's running now. If you've been waiting for the stream, apologies for the delay. Probably on Friday we'll often start a bit late because of the one tutorial session that's just finishing, and on the other end of campus to make things worse. Okay, the other thing you probably want today's attendance code. So let's do that. I'll move the screen away. You can see it on Slido if you need it. I will just leave that question open there. But I'd like to show you something about the continuous assessment. So if you go to our module website and scroll down below the units, there are the two programming puzzles. So remember, what do we have as assessments? We have 60% from the exam at the very end in January, some written exam. I said a few things in the first session. We'll talk more about it later. And you'll get some past papers as well. Then we have the class tests, the first of which is online, and you can do it over the next 2 weeks or 1.5 weeks from now. It's just a single quick question, but there will be 6 or 7 of these roughly in total. So each of them is just a part of it. That's 15%. Then 5% you get from clicking on Slido. Please make sure that you somehow allow me to connect it to your name, to your account on Canvas. And using your uni email address is the most safe way to do it. If you put your name in the same way as it is on Canvas on the official registration, that should also work. But sometimes there's quite a discrepancy between how the names show up on the uni system and how they show up on Canvas and how they show up when you send an email. For various reasons, it's just a fact. So the easiest is the uni email address because that's unique. Right, and the other 20% are split 10-10 to the 2 programming puzzles, the first of which is this one. So you can read over this in more detail. It's a made-up puzzle. I wrote a little bit of a motivational story, but it's mostly a joyful puzzle. I don't want to say too much about that because part of the learning outcomes is also for you to get an understanding of a problem deeply from just reading some formal specification like I wrote it up on the website here. And I don't want to deprive you of the opportunity to try to understand it on your own from the writing, because that's what you need to do if you read research papers or if you read books about cutting-edge algorithms that you may want to use in some graduate level jobs as well. So I won't explain the puzzle in detail here, but we can talk about it if you have questions. If something is unclear, of course, let us know on CampusWire or elsewhere in the tutorials or after class. The way this works is it's a specific general puzzle, and then there's a few concrete instances. And you're basically asked to produce good solutions for this. And you can come up with those by hand, or you can write code to do it. That's basically up to you. What you have to submit is a little piece of code, of Python code, but very simple if you do the solutions manually. Then you just type it in a little bit of a Python script. That's just for quickly checking the quality of the solution. Yeah. There's very little that you need to know about Python for this. So you can write your code in another language to produce the solution. And the solution is basically one list of numbers. If you want, you can copy paste that to the Python script, and that's all the Python you have to touch. Of course, you can use Python because it's the official language for the course, and there's this programming fundamentals module that some students take in parallel. So we converted things to Python for that reason, but it's not exclusive. You can use other languages to produce the solutions. There's basically 3 things that we ask you to submit in the end. One is your solutions, and these are produced by the Python code that you can download there. So you put your solutions in, the code computes a quality, and the resulting file is what you're supposed to upload to document the quality of your solutions. You should also submit your code so that we can reproduce what you claim. Basically, this is just the outcome, and then this might have more detail about this. And if you use some other codes to produce your solutions, you can submit this along the way just as documenting your work. And lastly, a short written report where you explain what you did. It's supposed to be just 1 page. We had much trouble with reading handwritten things in the past, and that was a big pain. So we decided only typed solutions are allowed. There's an optional part that you can have a look at. The puzzle is such that you can have solutions of different quality, and there's an optimal solution, but it might be very tricky to find out the optimal solution. Or you have a solution that looks good, but it's not clear if it's best possible. And you can try to prove some impossibility statements where you argue that a certain quality is not achievable. I've made this optional, though, because this is more challenging, and many of you are not so well experienced with writing proofs and so on. So this is optional because I think it makes the puzzle more interesting and more fun, but it won't be part of the marked assessment. I want to mention that the puzzle is a new open research question that came up in some of the work that Ben is also doing. And so we don't know the solutions for these. If you know what that is, it's very likely an NP-hard problem. So it's unlikely that there's a simple, fast algorithm that solves this in the general case, finds the optimal solution. But there's various ways how you can get some reasonable solutions with heuristics and other insights. But we don't fully know. And for some of the solutions, I don't think we know what the best possible solution is. So it's kind of open and gives you the opportunity to surprise us. That's why I started. Maybe you can even beat the best solutions that we found. So give this a read and let us know if you have questions. It's a bit of text and so on. I don't want to do it on the spot. It's also a lot of time. I'd have to look it up on Canvas what I put in. But you can see the deadline when you have to submit this. It's at least 3 weeks, if I remember correctly. So it's quite some time to do it. So no need to rush. We talked about the use of generative AI tools, and in this case, there's a specific statement what you're supposed and allowed to use and what not. So have a look at that as well. Okay, any immediate questions? Well, you probably need time to read it first. The positive thing to say maybe, it's an open puzzle, so it can be very hard to find the best possible solutions, but you don't need to find the best possible solutions. We'll mark it relative to how close you come to what we could find, but 100% is not the optimal solution, right? So you can, with fairly simple tricks, you will get most of the marks, I think. And then there's some room for becoming more creative, getting more insight into the problem. Does anyone still need the attendance code? I'll show it later in the break again. I'd like to put back the first question. So if you haven't voted on this, you can do. Okay, then with a bit of delay, let's start the lecture part. Welcome to Unit 3 of COMP526, Efficient Algorithms. We'll look at sorting in detail in this unit and a few other related divide and conquer algorithms. Much of this first part will be repetition for many of you, but then we'll have two more parts that go a little deeper, and is also touching on some of my own research, so it's kind of dear to my heart, the topic. But let's get started slowly. And before we get started, let's have on the record again the little overview of what sorting algorithms people already know. Bubble sort is really big. For some reason, bubble sort is always well known, even though it's by all means, by all standards, a not great algorithm. It's fairly slow. But it somehow is cute and has a good name, I guess. Good names are important. The other two big ones are quicksort and merge sort. We'll talk about these. And okay, many other little variants, more or less well known. Heap sort is, of course, another one. That is taking the binary heaps that we use to do sorting. If you haven't seen this, you can you learn a little bit about this in the tutorials. And we'll come back to this guy as well, radix sort. There's actually many more. It's sorting is somewhat of a standard toy problem that people love to invent new things for. Whether or not each and every one of them is useful is maybe a secondary question. This is often something that people do for fun. Some form of fun, I guess. For this module, what I'd like you to take from it is specifically merge sort and quicksort as the two most important and the most important efficient algorithms that are in wide use. Know what their performance characteristics are. And then we'll talk briefly about the lower bound for sorting. Again, something many will have seen in undergraduate computer science courses if you've done that. And we'll briefly talk about how you can break that lower bound. And then we'll look at what happens if you can exploit some existing order in the input. So there's the overview of the sections. At the end, we'll cover a few other divide and conquer algorithms, just to show you that many of the concepts that we apply to generate sorting algorithms are more general than that. It is insightful to have a few examples that are beyond sorting for that. Why still do sorting? First of all, it's a fundamental problem that still has unsolved corners. For example, an innocent question could be, what's an algorithm that uses the fewest number of comparisons to sort n items? And kind of tantalizingly, this is open. we don't really know. At least if you zoom in very closely, if you want to know an algorithm that exactly uses the minimal number of comparisons, that's open, and the last substantial progress might be from the 50s, 1950s, with a few improvements after that. But that's kind of the academic motivation. Of course, sorting is a subroutine that's used for many other more complicated algorithms or processing steps. It's a way to remove duplicates from a data set. There's other ways with hashing, but sorting might be faster in some cases. And many geometric algorithms, things like scanning line algorithms, often use sorting as a pre-processing. What we'll focus on here is the classic fast sorting methods. In the first part, just as a recap, how to exploit if the input has some structure to be faster. And we'll also talk about parallel algorithms and parallel sorting as one specific topic, but not in this unit. We'll come back later to parallel algorithms and then look at sorting again as one problem where parallel algorithms are interesting. Because sorting it's possible to parallelize it, to use several cores on a computer to sort, but it's not obvious how to do it. Before we start, let's cover a few basics and define what we mean when we say sorting. And for most of this unit, this will be the setup, with one exception that I'll comment on when we get to it. We'll work with arrays of objects, and I'll be generic what objects are. It could be anything. Think of some arbitrary Python object if you want. I've used this a little bit before, but just to state that formally again, if we have arrays, I use this kind of notation with dot dot to indicate that that's a range in the array, or that the array has this size. Python would probably rather have a colon and then the two indices. I'm trying to use this notation often where the first index is inclusive and the second is exclusive, which is exactly what Python would do with a colon. But I'll use these parentheses to make that visible in the syntax. Whereas it's standard if you use square brackets that it's inclusive on both ends. So that's just so that you don't misread the pseudocode that comes. What we assume as well is that the objects are somehow ordered. We talked about this for binary search trees and heaps already. It's the same assumption. So there's given two objects from our array, there's a way to tell which is smaller. Now here we'll be happy if this is just a lesser equal operator. So you can ask, is this lesser equal than this? Yes or no. That's what we'll work with. Python has, of course, this built in as lesser equal operator. You can override it for custom classes by implementing or overriding this function with a double underscore. I don't know if you're new to Python, maybe you don't know this yet. It's just a way to define the lesser equal symbol to mean something for your custom objects. Java has, as the second language that many people know, has a similar setup. So there's a specific interface comparable that you can implement. And then objects have a compare to method that behaves essentially, if you compare it with 0, it behaves like the comparison operators. So long story short, given two objects, I can decide which one is smaller. And then the goal is to rearrange them in the array so that they're in sorted order afterwards. So unless it's otherwise stated, we'll assume we sort in place. So we produce the sorted list in the same array that we're given as input. That doesn't say that some algorithms don't use extra memory to do the sorting. But at the end, it should be back where we started. Right, for the experts, we'll focus on internal sorting, which means methods that are effective if the input is fitting in main memory, small enough to be held in one computer and in main memory. So that would be a few gigabytes easily. On a large server, maybe a few hundred gigabytes. On a large server, maybe a terabyte. If it's much more than that, then you probably use different algorithms, and that's a separate topic that we won't touch on. We'll also assume for now, for this unit, that we're just doing everything sequential, single processor. Apart from asking you just for names of sorting algorithms, let's do the slightly more theoretical version of this. I will comment a bit more on what this question means. Had 111 people vote earlier. Let's see how close we get to that. I don't know why this picture showed up. I didn't intend the picture to be part there, but if you recall, that was part of the prior knowledge survey as well, and that's where that screenshot is from. Let's leave it with that, so you can see various answers. Yeah, if you sent the letter from before, then you'll have to look up what that stood for. Not very convenient to do. Yeah, sorry, I'll have to remove that image. That's just confusing. So the most voted answer was G. If I hide this again, G was order n log n, big O of n log n, and then various other things. So let me unpack the question first. There's a few things that maybe we haven't spoken about in full detail yet. I'm asking about the complexity of a problem. That's a bit of a weird thing to do, right? We've talked about the cost of running an algorithm, but this sorting is not an algorithm, that's a problem. It's an algorithmic task. So what do we even mean by complexity here? What algorithms people mean in this context is, give me the best you know about this problem, how fast can you do it, and what's the best impossibility result you know about that problem. And for some lucky problems, and sorting is one of them, we have matching upper and lower bounds up to a very small error margin. So we know precisely how well we can do, and we know ways to do that well. That's pretty striking. It's one of the things that computer science is fairly unique at. Show me some of the other engineering disciplines where you can have so close gaps between what's theoretically possible and what's actually achieved in practice. I always bring this example of a internal combustion engine, you know, a car motor. We know there's some physical limits like preservation of energy or things like that, but we're far away in the efficiency of actual machines, in actual engines from that limit. Computer science for sorting and other problems, we're right at the limit. There's a theoretical lower bound of how fast you can go, and we're almost matching it. That's pretty cool. So that's what people mean when they ask about the complexity of the problem. Give me the best impossibility result and the best algorithm that you know, and hopefully these are close. For sorting, well, we know that we can do it in n log n time. and we'll come back to that, of course. And we also know there's a lower bound of n log n. And those essentially match if you're only looking at the big O classes. So you could say the complexity is theta of n log n. And what this statement means, there's a lower bound of omega n log n, or impossibility result, you can't do better. And there's an algorithm that achieves this. And those two things together, so if you have these two, they imply that you can say the problem has this complexity. That's what you will read in more academic writing about algorithmic problems. I thought it's useful maybe to mention this. Now, we haven't talked about this, we haven't talked about this, so these are both results. I just claimed that these are known, but we'll actually cover them today. It's not so far away. Let's start with algorithms, because these are often easier to grasp and to understand. And I'll probably go relatively quickly through this, as it's repetition for many. But I want to give you a chance to show me how much you remember, or how much you know if you haven't seen it. There's many questions coming today. It's one of those topics where I don't have a good feeling for how much you know, so I'll keep asking you. So you'll have to tap a few more times. So let's try to do this one quick. And again, if you don't know yet, I'll tell you how it works. It's just the speed at which I tell you will be a bit dependent on this. If you haven't seen it, the same red book, I should have brought my copy. The red algorithms book, Sedgwick and Wayne, that is linked on Unit 2, is also covering all that we do in this first part. So if you want to read up the things at a reasonable pace for doing it the first time, that's a good source. Right, so most people, let me give this away. So most people get the second one. We'll talk about the first one too. And then there's a few with don't know, which again, that's fine. You may want to read up on it in a little more, in a calm moment. So let's do a quick rundown of merge sort on the conceptual level. I won't show you full code for the merging part, but that's again done in the algorithms book by Sedgwick and Wayne's in full detail. Conceptually, what merging does is you have two parts that are sorted. So these triangles just should mean elements increase in value. They're already ordered. So imagine this is your array, left to right is the indices, and the height is the value at that position. Suppose they are numbers. Again, the algorithms all just work for any type of objects, as long as you can compare them. If I give you two, you can tell me which is smaller. That's all we need. But to make the examples easier to grasp, I will often use numbers or heights of bars. So the conceptual view of merging is you have two sorted parts. They're sorted within, but you don't know how they relate. And you produce one big output that contains all the elements from the two parts and is entirely sorted. How does this look like in an example? Here are two runs. Again, elements by height. Height is what we compare. And you see they are sorted. These just go up. And merging just can proceed like this. These are sorted runs, so the smallest element in each of the runs must be the first one. That's the one where these arrows point to. So we have two candidates for the overall smallest element. And we just take the smaller of the two. That must be the smallest overall. In this case, it's that guy. And then we can just move that to the output. So we copy the element to a result space. So that will be extra memory as a buffer that we use in merging. Once that element is gone, there's another first element in that run. So we again have to ask, is this one smaller or this one, by comparing them. And again, the first run is the one that wins. So we write that to the output. And we keep going like this. So this time, again, we compare the first of the remaining elements of the runs. This time this is smaller, move it to the output, and so on. And sometimes you can take a shortcut if you've completely exhausted one of the runs. The rest you can just copy over because there's nothing else to compare them to. And that's basically merging. Now that's not sorting yet. We already needed two sorted parts, but we could produce from two sorted parts one big sorted part. That's what we've done so far. Before we move on, let's again probe your memories or your general knowledge. Where is my question? So let me point out, this is asking for merge sort, the entire thing, not just merging what I showed you the example for. All right, looks like a very clear picture. So let me just give this away. Okay, I didn't, maybe I scroll down if there were more answers. That's an absurd amount of possibilities. I just put everything in that might remotely make sense. N log n is the answer. I kind of gave that away maybe by saying that sorting has this complexity. But it's good to remember. So hammer it in a few more times, doesn't hurt. How do we turn this merging procedure into a sorting algorithm? The abstract explanation is what popped up in the Slido question. You recursively sort the left half. You recursively sort the right half, then you have two sorted parts, and then you merge those. And the beauty of recursive algorithms is that that's all you really need to think about. And that's what this algorithm does. So merge sort is given some range of the array, and the first call will then be merge sort with the entire array. So starting at 0, ending at n, if that's our length. That would be the initial call. Then we determine if we're already done. If we have if we have a list of just a single element, nothing needs to be done because that's sorted in itself. Otherwise, we find the middle point. So if that is our array from L to R exclusive, then we find this midpoint M. And we recursively sort the part up until M excluding M, and the right part from M onwards, and then call the merge procedure that I showed you by example. Now, that merge procedure needs an output buffer. It doesn't work directly in the array that we're given, and doing that is actually possible but very tricky. So you can do that, but it's slow, and so it's not very interesting. The fast merging methods use some buffer area to write the elements to. And then here we copy them back so that we have this outward facing interface of sorting in place. Okay. That's all the code there is for it. And it's not hard to implement that in your favorite language. And I'll leave that to you. You can see it in Java in the algorithms book. I'm sure there's an easy Python implementation to be found on the web. What I want to briefly talk about is the analysis. Why is this n log n overall running time? Slightly differently from what some other books would do, what I want to count here is the number of element visits. And so an element is visited whenever it is read or written to an array. Now, that's very related to the number of comparisons. If you think about the merging procedure, you read through one run, you read through the second run in interleaved ways, and you write the output once. So the cost for a merge, when you have two runs of length n, if the output is of length n, then the cost of a merge is 2 times n. And that's true in the best case and in the worst case. It doesn't matter how the elements look like. They always have to be touched, read and written. If you count the number of comparisons instead, you get something that's between n and 2n. So maybe worth writing down, but the analysis then will continue with this element visits as the elementary operation. Between n half. I guess at least our merge procedure, it would check, is the first run's first element smaller? Yes, yes, yes. If the first run always wins, you exploit the first run entirely. That needs roughly n half comparison, the length of the smaller run. And the second run doesn't need any comparison, it's just copied over. So this is still roughly, or upper bound is n. But the math is a bit nicer if you do the element visits. So you've looked in the tutorials at recursive ways to express a function or a sequence of numbers. And that's what we'll do here for the analysis. We say C of n is the total number of element visits to sort an input of size n. And if the list is short, is just a single element, we don't actually touch that element. We just return right away. So that costs us nothing. Otherwise, we do these two recursive calls. And if you work out how long they are, one is n half rounded down, and the other is n half rounded up. That's the cost. So we use the same function. So that's the cost for recursively calling us on left and right part. And then we add 2n for the merging. That's where this recurrence comes from. The second step is a pure math exercise, and you've done it a little bit in the tutorials for a simpler example. Here, one thing you can do is if you simplify by saying n has to be a power of 2, I'm only solving the recurrence for a power of 2. Then those two parts, the rounding always works out evenly, and you don't have to round. Then the recurrence simplifies to this, and you can actually spell out, you can explicitly say what happens. So you get the 2 times 2 to the k from the first part, from the merge at the very end of the algorithm. Then you have a first recursive call here, and that gives you this green term in the next level down. So you multiply it by 2, then you have 2 times 2, that's the 2 squared. But you go down in the argument by a factor 2. So that's why here, instead of 2 to the k, we only have 2 to the k minus 1. And if you observe what happens if you spell this out a few more steps, you see that that's always the same thing. You add a power of 2 in the front, and you subtract a power of 2 in the argument. So all of these terms are actually the same because the powers just add up. And so it has a nice closed form. If you reinsert, if you solve this for k, then you get k is log n. And inserting that gives you this solution of 2 times n log n. Strictly speaking, that's only true for powers of 2, right? So if you want a strict upper bound formally proven, you could say this function is monotone. It costs more to sort a longer list. So you can bound C of n by making n artificially larger, going to the next power of 2. And so you get an upper bound, which is a factor of 2 away, but it's still n log n. Now, just because it's so cool and I want you to know, you can actually solve this recurrence exactly. It doesn't at all look like it because of these weird rounding ups and downs. It feels like that's complete chaos. But no, you can handle the chaos and you get this precise solution. It's an equality, no approximation. Where you have the basic term that we found as well. The 2n log n shows up as the main term. But then you have a term 2 times n multiplied with something that's, I guess it's between 0 and 1. And it fluctuates depending on how close n is to a power of 2. Okay, that's just a piece of trivia. Treat it as the fun bit of that slide, and you can otherwise ignore it. But that's merge sort and its analysis, where we've used recursion to write the algorithm and to write the analysis. So knowing already that this will be the optimal time complexity, what speaks for merge sort is that even in the worst case, it has this n log n complexity or upper bound for its cost. It happens to be a stable sorting method. That's something we haven't talked about. It's still true. Stable means if you have elements that compare equal. So A and B, A is less or equal B, and B is less or equal A, which you could say A and B are equal. That can happen even though the things are not identical. So for example, you could have a list of people sorted by age, but they could be born on the same day or say same year or whatever, but not be the same person, right? So a stable sorting algorithm would keep objects that are identical according to the sorting criterion in the order they've been in the input. And that's useful if you sort complicated objects like people several times. So you could sort a list of people first by their first name, and then sort that list by the last name. If you do that with a stable method, you will get a list that's sorted by last name, and among those with the same last name by first name. And that can be useful. If you do that with an unstable method, if you sort by the last name of the second round, it might scramble the order of the first names again. So merge sort is easy to make stable by when you do the 2 runs and there's a tie, there's the 2 first elements that are equal, you just take the one from the left run and give that precedence, then you're stable. So that's good for merge sort. Another thing, this is getting a bit more technical. We talked about our model for computers. We said, okay, all we do is on the RAM, on the word RAM abstraction of a computer. Now, of course, we still have to eventually use the computers we can actually build, and they are not precisely that model. In particular, they have caches and a memory hierarchy. And so if you care about the performance in practice, it's another benefit of merge sort that it uses memory in a sequential way, basically scanning left to right, jumping one step at a time instead of randomly jumping around. And that just happens to be faster because of caches. That's not really something you need to know deeply for this module, but I thought it's useful to throw out. Now, merge sort has one big downside, which is that it needs this buffer space for merging. Remember, when we take the 2 runs, the only easy way to do merging and stable is to write elements to a buffer array. And that means we need extra space. I mentioned this before, there are ways to work around this, but they're mostly theoretical curiosities, not so much relevant in practice. So there's, as a puzzle, you can do merging in place and stable with complicated recursive tricks, but it ends up writing the data many times, so it comes at a prohibitive cost. But it's possible. Questions so far? There's a bunch of questions on Slido, and I think it's a good time to take our little break. So let's first do the break, and let's round it to exactly noon. And I'll check if we want to do questions straight away or do that after the second part. Okay, I'll try to be closer to the mic. Sorry, guys. You need that one again? Okay. It was a short break, but let me start with some Q&A. Go away attendance code. We have the deadline is one question. And there was the question also of putting it on Canvas. It actually is on Canvas. I've put these in straight away with the due dates. Now, for the second assessment, this is just an empty placeholder. You can't submit anything there. But for this one, you can. Okay, so let's pretend I'm this test student. This is, of course, my view of Canvas. And then so that's what it looks like. I think I already did this, but you can submit as often as you want for this one. So you can upload a snapshot, and we'll then decide at some point that we'll take the latest submission. So make yourself aware of the late submission policy. We'll always use the latest submission that you submit on Canvas if there's multiple attempts allowed. But if you submit one after the deadline, that means we'll have to use the latest one and you incur the late penalty. So just be aware of that. But you're welcome to submit something early. I'm actually encouraging you to do so. So you can submit and replace your submissions here, and you can upload files. So look at the website for what exactly you're supposed to submit again. That's listed here. And it just all goes, you're just uploading several files, but for the same assessment. So you should make a submission with all those files. Canvas is not able to check that. I can only allow specific file types, but I can't tell it to check, oh, I want one PDF and one zip file and one JSON file. I cannot do that. So you have to be careful that you submit all three in one go. There was another question. Let me highlight that. About GitHub Copilot is a useful tool. I mean, I like it for programming too. So I would say it's fine for routine code. Remember my long monologue about academic integrity and generative AI from the first session here. The goal of these assessments is twofold. It's one, to get you some mark, but also it's to give you a learning experience and to build skills. And you totally deprive yourself of the second part if you do everything with AI. So routine code would be standard functions that you definitely know how to code. You just want to be faster. Using Copilot to solve the algorithmic problem, I would discourage. Now, of course, I also tried before posting this, and what ChatGPT came up with was utter garbage. So at least as long as you don't invest much more time in polishing it, it won't be so helpful. And Copilot is based on similar principles. It will generate some code, but it won't solve the algorithmic puzzle for you. And that's good, because that's what you're supposed to learn and take from this assessment. So that was the other question. There was the question about tutorials. The tutorials are not recorded. Various reasons, but what we can offer is that you attend a different session if that is not oversubscribed. If for timetabling mayhem you can't attend your session, Ben tells me it's fine if you attend another one, as long as the room doesn't get too full. And the slides and the typed solutions will be posted. Right, you know that. I think I'll take this one offline, maybe ask it on CampusWire again. That's a longer discussion. My heart hurts that we don't have the time to discuss hashing in this module in any sensible depth. So I won't really talk about it much. Maybe I'll leave it in here. So that's a bit tricky to say. I think the problem is that without giving you without giving away what the solution is that we have, there's no real way to tell you how your solution would fare. Just try finding good solutions. I think if you spend some time with these puzzles, you get a feeling for either you're stuck with all the things that come to your mind to try, or you have an idea and then maybe it's worth exploring. I don't think it's oh, okay, I'll sit down another 2 hours on my bum and that will produce a new solution. It's probably not really like that. Both of these, the tutorial slides are supposed to happen on Campus Wire at some point. Same for the tutorial answers. So keep an eye open, or send a polite reminder to Ben for the unlikely case that he might forget. But I think he uploaded from the first week. I've seen something, and he will only upload the slides and solutions after all the tutorials of the week. Okay, time for a few more algorithms before I let you go for your weekend. The second big sorting algorithm we'll discuss is quicksort. In some way, it's related to merge sort and has complementary benefits and disadvantages. So it's good to have both of these around. Again, before we start, let's do a quick check of what you know. You see the pattern, so it's the same type of answers, same set of answers from before. Okay, let's slowly move on. And okay, so there's a majority vote, which is correct. But there's a few more people not so well familiar with quicksort, so maybe this is a good excuse to do this part a little slower. I'll come back to it. So similar to merge sort, we have one key step that we do, and then we recurse to make that into a sorting algorithm. For merge sort, that was merging. For quicksort, it's partitioning. And again, a pictorial representation of this could be like this. That squiggly line is supposed to mean there's no specific order in this array at this point. So it looks smooth, but it can jump around wildly. And after partitioning, there's a pivot point. So this point here, where from that point to the left, everything is below the value at this pivot point. And from there to the right, everything is above that pivot point. All right, so the important bit is nothing in here and nothing in here. That's what partitioning means in the context of quicksort. And let's see how this is done in a fast way on an array. It might not be exactly the version you've seen if you have seen quicksort before, but this is, quote, the right way to do it. It has stood the test of time and came out as the best option. First of all, we need a pivot element. So we start by randomly choosing the value that will eventually be this dividing line. And that's going to be a tricky choice, but for now, we'll just pick the first element out of better ideas. And for the remaining elements, we have to decide whether they are smaller or bigger than this element p and move them around accordingly. And we start with one pointer on this side. So if that element here is smaller than the pivot, that's fine. So it's smaller. That means we'll leave it where it is for now. It's on the left, so small should go on the left. Let me take the next one. This is larger than the pivot. So that means it has to end up in the right half of the array eventually. So at this point, we don't like it where it is, but we wait before we do anything with it. Instead, we now start with a pointer on the other end of the array and do the same game. But now this is a big element and it's on the right, so that's what we like, and we leave it where it is. Whereas if we find an element that is small but on the right, that's again something we don't like. And now we're in the fortunate situation, we have two elements that are both in the wrong side. Let's just exchange them. And that's what you do, and then both of them are repaired at the same time. And this kind of double progress that you make for one swap is what gives this method usually an advantage over alternative ideas how you can do this partitioning. Right, then the next step is just continuing the same way. So you take the next pointer, that's a small one, it can stay where it is. You continue, another small one stays where it is. Next one is large, so we have to move from the other side. So we start at the other end. That's a large one, can stay where it is. That's a small one, so we have again two ones that are wrong ordered. Swap them, then they're both happy. And at this point, you know that you're done when these two pointers that move towards each other have hit the same point. There's one last thing that you have to do to get this picture, which is swap the pivot in place of the last element of the first run. Now we have this nice situation, right? There's this line and this line, nothing in here and nothing stopping in here. Okay. A few remarks. We did not need extra space. All we needed was swapping elements around in the array that we're given. In a vague sense, at least, we visit every element only once, either from the left or from the right, either from the left or from the right, but we only touch it with one of the two pointers. And what we can do for free, this will become handy later, is return the position where the pivot is at the end. Because it's lovely to be able to partition the array in some way, but because we can't always guarantee where the dividing line is, it's useful to know where it ended up being. So we can return that from partitioning. I put detailed code for the partitioning procedure on the slide in this case, because unlike for merging, this code is surprisingly tricky to get right and has caused major performance bugs in the history of Quicksort. So Quicksort is a bit infamous for being tricky to implement correctly. It's not to say that it's an unsolvable task, but if you ever have to implement your own Quicksort, I highly recommend you to take an existing partitioning method, and this is one of the ones that is fairly robust against all sorts of performance issues. I can talk more about this offline if you're curious. It's an interest of mine, and I worked on this, but it's not relevant for this module. I just wanted to give you the definitive code in case you ever need it. What's left is turning this into a sorting algorithm. And now again, we have something that does part of it. It makes the array slightly more sorted, but it doesn't do the entire job. But what we can do is first do the partition so that we get into this situation where everything here is below, blah, 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 everything here is above. The key trick of partitioning is I can sort this and I can sort this part independently. It will never happen that one element that's currently over here has to move to the left or vice versa. Because they're partitioned, all the elements on this side are smaller than the pivot, so in sorted order they have to be left of that pivot. In code that looks like this. So let me just briefly go through it. Again, it's a recursive procedure, so we have some range, and the initial call would start with 0 and n. Then we stop if the array that we're looking at has only a single element, then there's nothing to do. Then we just return. Otherwise, we need a way to choose the pivot. And I left it generic here. There's some function that chooses some pivot from this range. A simple choice could be just pick the first element, like in the example. And that's an option, but I'll comment on it in a second. But there's some way to choose the pivot and get its position in the array. And then we call partition, where we tell the method, oh, please use this element as your partitioning element. Otherwise, it's as in the example. And what comes back is this position, j, where we have the dividing line between the two parts. And then we can sort the left and right parts independently. And that's all. So in quicksort, all the work is done before the recursion. In merge sort, all the work is done after the recursion returns. OK. It's also a recursive procedure, similar to merge sort. The choice of the pivot is fairly important and needs some thought, but I'll only do this very quickly here. One easy option is take the first element or some other fixed position, but that means you're potentially vulnerable to a bad worst case that someone might even exploit by explicitly giving you an input that makes you perform a long computation. Much, much better is a random choice. Then at least no one can give you a single input that will make you fail. This is very similar to binary search trees and the discussion of how high the random binary search tree is. And indeed, there is a deep connection that we'll come to. What often is done in practice is something in between. So for some reason, programming libraries shy away from using randomness. They prefer to have things deterministic. So instead, people use something that is at least not quite as risky. You take 3 elements and take the middle one of those as a pivot. That is likely to be better than taking a fixed position and has a few benefits, but it still is somewhat vulnerable. But these are the options. Before I tell you more about the analysis, let's see again what you know there. This is also a welcome starter question for exams. One possible such question. Okay, again, way too many answers to fit them on the screen nicely. Okay. Let me show you. There's various bars, and majority got it right, but it's a bit of a trick one. So definitely remember this one. Like if you take nothing else from this subsection, that's the one piece of information to keep. But I hope you take more, because there's a lot more nuance to this. So the right answer, first of all, is n squared, much, much worse than n log n. I want to keep you, once in a while, I want to say a few things outside of the formal context. Log n is way smaller than n. And hence, n log n is way faster than n squared. OK, maybe that's obvious. Just if you look at the terms, what's the big deal? If you actually run things, it's such a big deal. OK, before we come to why that is the n squared worst case, I want to show you instead some connection to something we've already seen, and then we can recycle knowledge. That's cool, right? We don't have to work twice. We just have to make the connection. So let me show you the connection in the nice way, where I'll cheat a bit in the partitioning method. If you catch me cheating, you can show. I can comment on it offline again. So let's have a quick example of how quicksort sorts this list. It picks a pivot, and I'm assuming here I pick the first element. Just to make the analogy nicer, it goes through in general. I'll take all the smaller elements in the left, all the bigger ones in the right, and the pivot goes in between. I'll give away the cheating that happens. This is not using our partitioning method where I showed you the code. It's one that is a little nicer to analyze. But the same arguments would hold true. It's just less transparent. Okay, so forgive me for that one. But I think you'll like the rest. Now that's not done, right? We have to recurse on this part and then this part for sorting. So we do that, find another pivot, and again split into the elements smaller, the elements bigger, and the pivot in the middle. That's not what I wanted. Jumped all the way to the end. It's a long deck of slides. Yeah, I've done that, been there. Good, so we've been here. Then we partition this. Again, pick a pivot. This time there's no elements bigger, but that's all right, that happens. If you keep doing like this, you get this kind of, well, picture. Now, let me put these lines in just for fun of it. That's basically the recursion call. So we have one recursive call that splits the entire list, and it is left with that pivot element, and then has a left and a right recursive call. So it does two more recursive calls. So I'm just drawing the recursion tree, but I'm putting as the element representing that recursive call the pivot. Okay? Good. Without much explanation, let's take these elements and insert them into a binary search tree with our procedure from last time. 7 is inserted first, so it becomes the root and stays the root. Then 4 comes, it's inserted, is going to the left. 4 is inserted, is smaller than 7, smaller than 4, so it's inserted at this spot. Okay, you see how this goes, and if not, watch the videos from yesterday again. So you keep going like this and insert them in this binary search tree. And you see the left and right picture is the same, right? This is the same shape here as this. It's the very same tree. Isn't that somehow interesting? Is that a specific example where this happens? No, this is always true. If you build the recursion tree like this, you will always get the binary search tree that you would have got if you take the lists that you're sorting and insert them in the binary search tree. In fact, quicksort and binary search trees are very intimately related. They're almost the same thing, just doing things at different times. If you even look at the exact comparisons that are done in quicksorting that list, or inserting the elements in that order into a BST, it's the same comparisons. They just happen in different order. Forget about this part. That's the part I was talking about. This is not so important for us here. So what this means is, by and large, to analyze quicksort, we can analyze binary search trees. And we've already talked about those. I haven't shown you the analysis, but I made the appropriate claims. So that also means the worst case for quicksort happens if the recursion tree looks like this, or the binary search tree that you get looks like this. The comparisons you need to build this is you need one comparison, no comparison for the first element, 1 to get the 2 down there, 2 to get the 3 down there, 4 to get the 4 down there, 5. So you're summing up the first so and so many integers. That's this sum. That's the famous little Gauss allegedly discovered that formula in primary school and so on, but it's quadratic, and so that's very slow. Now, the easy fix is doing randomization. If we choose the pivot at random, that is exactly the same as if we were building a binary search tree with random insertions, because the two are essentially mimicking each other. The very same thing happens. And so if you do this, or if you assume that the input is shuffled before you go, So I went over this quickly. An easy way to simulate the same thing is to, before you start sorting, you just randomly permute your array. You randomly shuffle it. Then you can also enforce the average case for quicksort. And you can show that the exact number of comparisons you need is roughly this. Again, this is our friend from Unit 1, the tilde approximation, so asymptotically equal. And you can prove statements like this. If you want to know how likely is it that quicksort uses not 1.39 n log n, but 10 n log n or more comparisons for your sorting of a list, then you can show that that probability goes down if the list grows like this, 1 over n cubed and n squared. Yeah. Yeah, so when I say random pivot, that means whenever you do a partitioning step, you choose the pivot randomly from the range at every recursive step. So that's why it might be faster to do the shuffling at the beginning once and for all, and then not worry about randomness. Depends on details. But if you want to pick the random pivot, you have to do it in each step, at least for this result to be literally true. The intuition behind this, again, this is a lot of math behind this that I won't get into. The intuition is for quicksort to go bad or for a binary search tree to be really tall, you have to be not just unlucky a few times, but constantly. Like in quicksort, you would have to have a pivot that's very close to the smallest so that you keep this long list in the next recursive call. And then it happens again that you only split off a very small range. And you have to keep going like this for a very long time. And that's just very unlikely because each time you're picking something random, but I'm telling you, no, you actually got something at the extreme ends. And that's unlikely to happen. The further you go down, the less likely it becomes. So to wrap up on the discussion of quicksort, this is not something that follows from what I've shown you, but if you do experiments with implementations, quicksort turns out as the fastest general purpose method. It's usually a bit faster than merge sort, at least on random inputs when there's nothing to exploit. The average case is n log n. That's just restating what we had here. In expectation, if you randomize the input order, or on average, if all input orders are equally likely. It doesn't need extra space. That's the big boon over merge sort, apart from being slightly faster often. It doesn't need this buffer array. It's just the test. Yeah, it's great to schedule that during lectures, but what can you do? It's the scheduled test, so don't worry. The bell still works. We're safe. So quicksort doesn't need extra space. That's a big advantage. Like merge sort, the memory access is sequential in the sense that you walk over the array without jumping around. So that's the same. Unfortunately, it has this worst case that we can't really discuss away. It's very unlikely, but it's a possibility. So sometimes that's a problem. The other downside is it's not stable, and it can't easily be made stable if you keep in place. Again, as a theoretical puzzle, you can make it stable and in place, but then it's slow, so it's not really something to go for. The typical implementations of quicksort are not stable. And I would even put it as an open problem. In a way, that's also interesting. Nobody really knows a simple algorithm that is explainable on a few slides like this, that's fast in practice and is stable and in place at the same time. It seems these two things just are hard to combine. That's all on quicksort, but we started substantially late. So I would maybe discuss this lower bound. It's not much material, maybe 10, 15 minutes at most. Is that a big problem for anyone? We started much later. I don't want to push things too far ahead. Otherwise, we might have to delay some of the follow-up stuff. Okay, let's try it. So maybe I'll skip the Slido question in that case. In the next section, I want to discuss a lower bound for sorting an impossibility result. That basically implies that the two methods we've just seen, merge sort and quick sort, are almost best possible, but in a specific sense. And I want you to dig behind this superficial statement so that you know what it means. A bit in more detail, a lower bound in algorithms is usually a synonym for it's a synonym for an impossibility result. There's no algorithm that can do better than a certain performance, and it has to be mathematically proven. So it must be a rigorous statement. And in that sense, it's a super powerful concept, because it means if you have an algorithm that's close to that bound, you can stop searching, right? So a bit, I compared it to this conservation of energy principle in physics earlier. That's the kind of generality that we're hoping for. It seems to be somewhat unique for computer science to get so close to these lower bounds. You will often hear this algorithm is optimal for that problem. I don't love that term, because it often hides things under the rug. It's often better to unpack what optimal really means. And the whole point of this and the next subsession is to make you a bit sensitive to what's hidden behind when people call an algorithm optimal. Right, but what do we have to do to prove such statements? I want to point out that this is essentially a statement for all algorithms. It holds that their running time is at least this or this. That's the kind of statement we're looking for. So we need to prove a statement for all possible algorithms. So that's quite a tall order. And in particular, we need a notion to say what are all possible algorithms. So any lower bound assumes a model of computation necessarily. It could be, if it's powerful, it could be the RAM model, the one that we discussed for analyzing algorithms. But often lower bounds restrict computation to something even more primitive, just to make reasoning about the model easier. And that's what we'll do here as well. What we'll use is the comparison model, which is a standard model also outside of this specific use case. This model says, okay, I'm abstracting very much away from computers, what they actually do. I only count when they compare two objects, but that's also the only thing they can do. So I can take two objects in an array, I can compare them, and I'll tell you which one's smaller. And you can move elements around, but I'm not going to charge you for this. So the cost for running an algorithm is just these two operations. I don't charge you for how to come up with your decisions. You could even say the lower bound we'll use is even more strict. It only counts the comparisons. It doesn't care at all about moving things around. So this sounds like a silly machine, right? We don't have computers that work like this. But for lower bounds, that's kind of good. This makes very few assumptions. You can build many different machines that can compare elements and move them around. And for a lower bound, that's good, because it means the statement we'll get is more general. So usually for algorithms, a more detailed model is better, because then you can model reality closer. But for lower bounds, the opposite is true. The important bit here is that both merge sort and quick sort are inside this model. You can formulate them so that they only work by comparing elements and moving them around. We've basically done that in my high-level explanation anyways. So they're part of this model. They're captured by what we'll say. And now comes the big important step. So this is the key insight that we have to take. I don't know. How can I highlight this without cluttering it up too much? The model has this nice property that we can say what algorithms in this model look like. Specifically because they're only allowed to compare elements, all they can really do to base decisions on are comparisons. And comparisons, in this model, this is only one type of comparison, say less or equal. So it has two outcomes, yes or no. And then the algorithm is not allowed to do anything else with the objects. So everything it has to do with moving them around has to be based on the yes or no answer from comparisons. So in that sense, we can model computation by having comparison nodes where there's two possible outcomes. And then the algorithm branches in two possibilities. It either follows a left or a right path. We ignore any movement of data in between. So instead, we'll only look at the comparisons. And what next comparison is done can, of course, depend on what you've done before. So you have two different subtrees. But that's pretty much all. Let me show you an example. I think that's clearer. So this is for a very small array for 3 elements, one possible algorithm in this comparison model. How does the algorithm work? It starts by comparing the first 2 elements, position 0 and 1. And what are denoted below the nodes is the possible orderings of the input that are still feasible or compatible with where we currently are. So I compare the first 2 elements, and the 2 outcomes are either A0 is smaller or not. Then you can filter out what that means for the different input orders. And in this case, the algorithm doesn't actually change what it does. It does the same comparison in both cases. So if A0 is smaller than A1, it checks if A1 is also smaller than A2. If that is the case, then the input was already sorted. We know that then. And the algorithm could then decide not to rearrange anything. Otherwise, if we go in this branch, so we know A0 is smaller than A2, but A1 was bigger than A2, then we still have to compare the first and last element. And depending on how that goes, we know that the input had this order originally. And in both cases, the algorithm could then decide, okay, now I know what to do, and just reassign the elements so that it becomes sorted. That's how so this is how in the comparison model algorithms look like. They're comparison trees, where the nodes tell you, these are the 2 positions in the original array I want to compare. Those are the 2 outcomes, and depending on that, the next thing happens. The important bit is that every algorithm in the comparison model can be formulated as such a tree. So we have a way to reason about all possible algorithms by studying all possible trees. And trees are much easier to handle than general algorithms with whatever complicated code. And now comes the step where we use this knowledge, what all algorithms look like, to get an impossibility statement. First of all, this is one concrete algorithm, but it's the algorithm shown on all possible inputs in the tree. If I have one specific input, for example this one, what will happen is that I always follow this path down the tree, because that's what actually happens if I call the algorithm with this input. So one execution of the algorithm is a path from the root down to a leaf. And on every step, I make one comparison, because that's the way we defined this tree. Every step down is doing one comparison, and nothing else happens in between that we count. That means the height of the comparison tree is the maximal number of comparisons this algorithm ever does on any input. In other words, that's the worst case number of comparisons that this algorithm does. But that's still talking about one concrete algorithm, this kind of tree that I drew here. The next piece is These are binary trees. I only have two outcomes. And we've talked about this before. If I have a binary tree with a certain number of nodes, I can compute how tall it has to be. I can lower bound its height. Here it's very slightly different. Instead of having the internal nodes, we have the number of leaves, but it's very similar. It's even easier in a way. If you have 2 leaves, then you need at least height 1. If you have 4 leaves, then the most balanced thing seems intuitively to give you the least tall tree. So the height, if you have L leaves, is at least log L, because whenever you get one step down, you can at most double the number of leaves. That's all that's behind this. So we now have a statement that if we have a number of leaves, we need a certain height. The last thing to nail this down is, again, now using something about the problem we're trying to solve. We're trying to sort a list of n elements. Now we need to do a little bit of combinatorics. How many different orderings are there if I have n elements? The numbers 1 up through n. There's n factorial of those. N times n minus 1 times n minus 2 and so on. Many different ways to see this, but you could say I first pick the position for the largest number n. I put that somewhere in my array. Then I have n minus 1 choices for the next number, for the number n minus 1. So I'll put n minus 1 in one of those n minus 1 choices that I've left. So in each step, I have one less choice, but each of those I can combine. That's what n factorial comes from. So a sorting algorithm needs to work differently on every different input or permutation. It's supposed to sort the inputs, so the output should always look the same, irrespective of the order original. So it has to do different operations. Otherwise, it wouldn't end up with the same state from a different input, right? Sorry, say it again. Yep. So the way to read this, that statement here is saying we don't have more than one of these orderings in any of the leaves. To turn this into a sorting algorithm, this is basically just the reconnaissance stage. It's just the recon part, learning in what order the elements are. And then you would have another step that rearranges them into sorted order. The important part is the rearrangement needs to look different for every possible input order. Pardon? Yeah, here it's already sorted. Here I have to swap the last two. For each of those, you can define a number of swaps. Let's maybe take it offline. The key point here is you need a different leaf for every possible input permutation, because you have to act differently to turn it into sorted order. So that means if we want to sort n elements, we have to have n factorial leaves. We know for so many leaves, we need log of that as height. And log of n factorial is roughly n log n. You can upper bound it and lower bound it. To be more precisely, you can give statements like this, but that's not my key point. It's enough if you keep that in mind and that it's asymptotically equivalent to n log n. So that means, what does that mean? That was the lower bound on the height of the comparison tree, on any comparison tree. And the height was the worst case number of comparisons. So that means any algorithm, any comparison tree, any algorithm in the comparison model must do at least n log n comparisons in the worst case. Merge sort actually achieves this, including the right constant in front of the leading term. So it's, in that sense, including the constant factor, it's optimal for comparisons. Yes, if you want to zoom in a bit closer, it's still open whether we can do this. There's a Slido question looking at the concrete comparison tree. I'll leave that for you to have a look at home. It's not so vital. So let's leave it with that. Just to recap again, very briefly, the steps. We formulate a model for all algorithms. In this case, that was all comparison trees. We use something about the problem that we're trying to solve, sorting in this case, to argue that all these programs have to have a specific shape. In this case, all of them need to have many leaves. And then arguing from the shape of the programs that it's a binary tree, you can tell something about the cost. And that gives you a way to lower bound the cost. So every algorithm in this model needs to use so many comparisons. All right. Next time we'll see how to break that lower bound in a specific sense.